So let's talk about triple integration in spherical coordinates. So again, this is another way of thinking about how to, basically set up your boundaries utilizing a different coordinate system, the spherical coordinate system, which sometimes is really very handy, especially if what you're working with is things that are spherical objects. And sometimes, like, if you're working on globes or like anything that, actually has, any kind of like circular or round or really round orientation, spherical can be really powerful and really handy. Where we're going to start out here is we're going to start out talking about the basics of the spherical coordinate system, just reviewing that a bit. So we're going to have our X, Y, and Z axis. I'm going to draw the X, Y, and Z axis. Remember that what we've got is we've got an r theta plane, okay? And in spherical, we're going to continue to have this r theta plane called, like the XY plane also can be called the r theta plane. And in spherical, it's going to be called the r theta plane, all right? So basically, that's the plane where z equals 0, okay? And it's that plane right there, okay? And so what we're going to do is we're going to have three coordinates. We're going to have we're going to have r, okay? And this is the distance from the origin, or actually it's rho, rho. It's the distance from the origin to, it's going to be the distance from the origin to a point in space. So basically that's a radius, but this radius is different from r in that rho we can go out in 3 dimensions, right? So we can imagine that this whole length here, now that's going to be rho. Or we could have rho, and rho actually is also on that r theta plane. So here's rho, okay? That could be rho. So rho is that distance from the origin to a point in space. If we were to write that, rho would end up being the square root of x squared plus y squared plus z squared. All right? Basically, it's the distance formula. That's how we actually find rho. And we'll talk about this a little bit more in a minute. Then we also have theta. Okay? And theta is exactly what we were getting when we had the r theta plane. Theta is going to be the measure in radians. Okay? So it's the measure in radians with 0 radians being the positive x-axis. So in general, when we talk about spherical, we are going to be talking about between 0 and 2 pi, and that's going to be essentially what we're going to be seeing is we're going to see this here is your theta. Okay? That's theta. And then the last set of coordinates is something called phi, right? So that's phi, or if we wrote it phonetically, phi. And what phi is this angle right there. That's phi. So phi is, if we take the positive z-axis, okay, it's going to be the angle between the positive z-axis and the vector that ends in our point. Okay, and so that's phi. It's a little bit trickier to think about, but if you kind of think about it, it gives you everything that we could possibly want, right, instead of a coordinate system. So there's phi. Now let's actually just draw in some points here to make things, to show what we mean. Okay, so you can kind of get a sense of how this works. Okay, and so like let's imagine that we have, say for example, we're going to have the point, and it's going to be rho theta phi. Okay, so let's go have that point be, let's have rho be 3. We'll have theta be pi over, let's do pi over 3, and we'll have phi be pi over 4. Okay, so I'm going to imagine that I have a vector. And I actually kind of like to, when I'm doing spherical, or I like to think about my directions first. So I'm going to imagine that I've got a vector pointed essentially straight up, okay? All right, and I am going to have, it's going to go out pi over 4. So let's imagine that's about pi over 4. Well, maybe a little bit more. Let's say pi over 4. So there's the vector. It's going to go out pi over 4. And then I'm going to circle that vector around pi over 3, because that's the theta. So that's going to be going in that xy plane. So pi over 3. So we kind of imagine, I always do this. It's now going to be kind of in this position right here. Okay, because we basically moved it in this direction. So it's going to kind of moved out here. If you kind of imagine, it's got like this thing kind of going out there. There's pi over 3. And then its length is going to be a length of 3. So we've got to have 1, 2, and let's lengthen it out a little bit. Let's 1, 2, 3. And so there's, it's going to be right there. There's our value, okay? And there's our value space, okay? So I always imagine, what I imagine when I'm drawing something in spherical is I imagine I've got a vector, okay? I'm going to first figure out, I'm going to kind of go backwards. I'm going to use phi in order to move it away from the z-axis. Then I'm going to rotate it around that z-axis in the theta direction, and then I'm going to extend it out to its length, which is the value for rho. So one more time, we'll do p, and let's say, for example, -1. We'll do pi over 6, and let's do, let's just do pi. Let's do pi. Yeah, pi. Okay. And this is going to look, well, how about this? Let's do 3 pi over 4. There we go, 3 pi over 4. So what I'm going to do now is I'm going to take 3 pi over 4. So 3 pi over 4, I've got my vector. I'm going to move my vector down 3 pi over 4. So it's going to go out to about there, let's say, roughly. So that right there, that's going to be 3 pi over 4. And then I'm going to move that vector, okay, I'm going to move it pi over 6. So you want to imagine, right, we're basically going to be moving, let's say that's pi over 6. And so if I move this directly down, this vector is going to kind of be, it's going to be right about there. In 3 dimensions, it's kind of hard to imagine, but there you are. So we move that. So that's now pi over 6 in that direction. Okay. And now it's -1. And so since it's -1, it's now going to go directly in the opposite direction now. Okay. And so we imagine it's going to be, it's of the length -1. So it's kind of going this way. There's a -1. Okay. All right. This is all just visualization. Drawing these points can be kind of like difficult in 3 dimensions. So it's really kind of, you just want to imagine what happens when we move, and just in general, how things happen or occur inside of 3 dimensions when you're working in spherical. So now what we're going to do is we're going to do some conversions from spherical. So we want to kind of think in terms of our relationships. So just, I'm going to set up, and that's x is going to be rho sine phi. Okay, rho sine phi cosine theta. Y is going to equal rho sine phi cosine, or sine theta. Okay. And z is going to equal rho cosine phi. Okay. So z is going to equal rho cosine phi. Now, if we kind of think through how this is like the relationship between the rectangular coordinate system and our spherical coordinate system, or excuse me, it's cylindrical, what we're going to get here is 1, so converting to cylindrical, right? 1 is that we get that theta equals theta. So theta is going to equal exactly the same, okay? If you remember our z is just going to end up equaling rho cosine phi, okay? And then we need that r is going to equal rho sine phi. Okay, so r is going to end up being rho sine phi. And if you kind of think about it, this makes sense, right? So if we imagine we've got our figure here, okay, and here is phi, right? Remember, phi is this distance right in there, okay? And if you kind of imagine that what we got is we're going to draw a right triangle, okay? We're going to draw a right triangle. This is going to end up being rho. Rho is that distance. Here is rho cosine phi, and here is rho sine phi. And right? Because that's just, it's a right triangle. That's what we get. And so if we project this line, rho sine phi, down onto the r theta plane, what you get is you get the distance r. So r equals rho sine phi, and that's why that works that way. Okay? So it's just basically, it's a, you imagine that you've got this right triangle that gets built in space where, you know, the hypotenuse is whatever the vector that you're looking at, rho is the length of that vector, okay? And phi is the angle, phi is this angle. And so if you take the opposite side and project it down onto the r theta plane, you get r equals rho sine phi, okay? And you can see, right, how we get r cosine theta, right? Because if x equals, so like our conversions here, from, like our conversions from rectangular, if we get x equals r cosine theta, then, and we substitute the rho sine phi, this is going to be then the rho sine phi cosine theta. And that's also the reason why in the y, we also have the rho sine phi cosine theta. So we get y equals r cosine theta equals rho sine phi cosine theta. Okay? And then z equaling cosine r rho cosine theta, that just comes in from here, right? That's the value for z, okay, in terms of whatever this vector is, right, that we have right there. Okay? So z is just that z ends up being the adjacent side to the angle phi. And that's why z equals rho cosine phi. Okay? If we want to go in and we want to convert from spherical into rectangular, so we got, there's our rectangular into spherical, which is what we're going to do mostly here. Spherical to rectangular is going to look like this. First, we know that rho squared is going to equal the square root of x squared plus y squared plus z squared. Okay? Or actually, what is this? This is rectangular to spherical, excuse me. Yeah. We also know that if we get, we have theta, we know that theta is going to end up equaling tan inverse of, tan inverse of y over x. Okay. And then phi, the value for phi is essentially, if we kind of think about it, what's going to happen here, this value for phi, why don't we'll use the cosine phi piece here, okay? So we'll write that z equals rho cosine phi, okay? And so rho is equal to the square root of x squared plus y squared plus z squared. It's that distance, okay? So z equals the square root of x squared plus y squared plus z squared, okay? And times cosine phi. So if we just actually solve for phi, what we get is we get that phi ends up equaling the arc cosine of z over the square root of x squared plus y squared plus z squared. Okay? And so that ends up becoming the value for phi. So we got rho squared is going to equal, rho is equal to the square root of x squared plus y squared plus z squared. Theta is just like it was in polar, tan inverse of y over x. And phi is equal to cosine inverse z over the square root of x squared plus y squared plus z squared. So now let's think about basic surfaces. Why is it this really matters? And so if we start out and we imagine a sphere, and hence why the name is called spherical, is simply the set of all points, right, okay, that are equidistant from, or that are equidistant from a certain value. So a sphere centered at the origin, right, so we want to make sure that the sphere is centered at the origin, is going to end up being just rho equals c, okay, or k, where k is a constant. And it makes a lot of sense given the fact that, okay, given the fact that rho equals the square root of x squared plus y squared plus z squared. And so that basically just says everything that's the same distance away from the origin is going to be the sphere. And so you just imagine you're just kind of moving all in the same direction. Okay, right? Everything moving back behind it as well. Okay, terrible looking sphere. And there we go. All right, there we are. There's your sphere. Not the greatest sphere. You can imagine that ellipsoids actually might be kind of handy to draw there too. Then also we have, right, so that's rho equals some constant. Then we have a half plane, okay? And a half plane, just like we saw before when we were looking in cylindrical, a half plane is simply, right, we'll just choose a value. There's theta. Theta equals something. Theta equals alpha. And then that gives me a half plane that actually goes through the z-axis, okay? Half plane moving through the z-axis is something of the form theta equals alpha, okay? That's a terrible plane picture, by the way. Just use your imagination on that one. I've done far better in past times. All right, now next up, we want to talk about cones. And so if you think about what a cone is, imagine that you've just got this vector. And this vector is, we've got this constant angle. And that constant angle is going to be phi. Okay? So this constant angle phi, and then we just, any value we want for r, okay? Right? So we can go out ad infinitum, right? And also in the negative direction. Okay? So you're going to get essentially this is, and this is like your phi, okay? And what that does is that leaves theta, or excuse me, theta and a rho free, meaning that they can equal whatever we want. And so consequently what we end up with is we end up with cones. We end up with this cone that's infinite dimensional. Okay? There we go. Not infinite dimensional. What I meant was it's infinitely sized. It goes up as far as we want, goes down as far as we want. We end up with this cone. All right, now let's get a super basic idea of triple integration in spherical. So what we've got here is we're going to imagine, right, just like we've done in every other triple integration, we need to figure out what dv is, right? We're looking for dv, right? And that's a big question for us because that's actually pretty much like the end result. That it's just a function, dv, right? Triple integrate, done, finished, right? So what we want to imagine is that we've got like a volume in space that we've actually decided to write in spherical, all right? And so when we do that, what we can do is we can subtend it. We can break it up into pieces that are basically these spherical boxes, okay? So they're spherical boxes. We'll call it this box is going to equal, and it's going to be rho theta phi, okay? And then we'll have rho is going to be greater than or equal to a and b, okay? Theta is going to be somewhere between alpha and beta, okay? And then because phi is, right, phi is also a Greek letter, we're going to have it going between, something in psi. Gosh, you know, should have rushed to fraternity. I think it's gamma and psi. All right, whatever. It's this thing and that thing. You want to call it C and D, it's also good with me too. All right? So basically, that's going to be our box. And so if we look at that, let's kind of think about what's happening here. So we've got this little figure right here, okay? And that's like one of our boxes out of our bigger volume. And so we've got here, this is going to be delta phi, okay? So there's delta phi, and then this thing right in here, okay, or actually right in between there, that's delta theta, right? So that's my delta theta, right? It's between those two values. And then I'm going to have delta rho, and what you want to imagine that delta rho is this thing right in here, so that's delta rho. Okay, there's delta rho right there, and that's basically the length of that, the length of the side of that box. Now, this length right here, okay, that's actually an arc length, and if you remember, an arc length, that's actually going to end up being rho delta phi, okay, because the angle that we're subtending, or the difference in the angle, right, which is actually this thing right in there, is delta phi, okay? And then we multiply that by the length, and that's going to be rho. So that's rho delta phi. And then I want to imagine I've got this thing right there, and then I've got this value. So this right here, okay, this right here. So that's going to end up being, this is, if you think about this, if this is phi, okay, then this length here is rho sine phi, right? Because it's the adjacent, or excuse me, this is rho sine phi. There's rho sine phi. And if we actually project that down onto the ground, okay, or down onto the side here, that means that this entire length right here is going to end up being rho sine phi. Okay, so there's rho sine phi. Okay. And if what I do, so there's that length, and I'm going to actually figure it out along the line, that's delta theta. So what that means is that this length right here, okay, is going to be rho sine phi delta theta, okay? Because again, that's going to be my my arc length, right? My arc length is basically the angle times the length, okay? And so there's my arc length right there. So if I multiply the three sides together, by the way, that's that thing right there too, because that's basically just a projection down onto the r theta plane. Okay, so there's that projection. So what we get here is we've got one side is going to be rho delta phi. We've got one side is going to be rho sine phi delta theta. And the third side is just going to be delta rho. Multiply the three of those together, you get rho squared sine phi delta theta delta rho. Okay? Or we could write that as delta phi, or excuse me, we'll write it as, our standard way is to be delta rho, delta theta, delta phi. Excuse me. All right? And that is, we'll call that delta V, right? That's basically your delta V. So what that means is that dV is going to end up, our dV that we're going to actually put at the end of our integration is going to be, dV is going to equal rho squared sine phi d rho d theta d phi. Okay? Which we could put in any order that we really want to, but in this case, we're going to put it in this order. This is our standard order, and that ends up being the value that we'll put on the end of our triple integral. So our triple integral is going to end up being, we're going to integrate, okay? So phi is last, so we're going to go from gamma to psi. We should just change it. Theta is going to go from alpha to beta, okay? And rho is going to go from a to b. And then we're going to have our function f of rho theta phi rho squared sine phi d rho d theta d phi. And that is our triple integral in spherical. Okay? Again, you know, the process is basically the same. You take this piece here, you take an arbitrary point that you pick inside of your mini volume, okay? We sum all those up, take the limit of those sums as they go to infinity, and you end up with this. That's what you end up with. Okay? All right. So let's make this rigorous. So Fubini's theorem for spherical coordinates. Darn it, Fubini, man. Guy's got a lot of calculus. Famous guy. If f of rho theta phi is continuous on a spherical solid box, b equal ab alpha beta gamma psi, then the integral over b of f of rho theta phi rho squared sine phi d rho d phi d theta is equal to the integral from theta equals alpha to beta, theta equals gamma to psi, rho equals a to b, f of rho theta psi rho squared sine phi, or rho, not psi, rho theta phi, rho squared sine phi d rho d phi d theta. Whew. All right. And you can integrate in any order that you'd like to. Okay, just as long as you correctly write each one of the values of rho, phi, and theta in terms of the correct equations. Okay, so just like the other equations, it says, hey, you can switch up the order if you need to. Make it as easy or as hard as you want to. All right, so now let's take a look and what we want to do is we want to get some examples. How do we set up these integrals, okay, to integrate? So let's set up an integral for the volume of the region bounded by the cone z equals the square root of 3 times x squared plus y squared, and the hemisphere z equals the square root of 4 minus x squared minus y squared. All right, first things first, why spherical? Okay, well, remember, take a look at this. This is, this right here, that's a sphere, okay, and that's a cone. And if you remember, spheres are really easily stated, like a sphere in spherical is rho equals some constant, and a cone is phi equals some constant. Okay, so we've got rho equals some constant, we've got phi equals some constant, and basically that's going to kind of really help us a lot in terms of setting up this integration. Okay, so we want to find the volume of the region bounded by the cone z. So what we're going to have is that means that f of rho theta phi is going to equal 1. Okay, because we're finding a volume, so we don't have to, basically the volume is just go find the triple integral. Okay, and so we've got this cone, z equals the square root of 3 times x squared plus y squared, and the hemisphere z equals the square root of 4 minus x squared minus y squared. First thing I'm going to notice about this, I'm going to say, okay, well, z is, so I got z equals the square root of 4 minus x squared minus y squared, okay? And so that means that z squared plus x squared plus y squared is going to equal 4. So what we have here is we have the cylinder, or the half cylinder, rho equals 4, okay? There we go. Rho equals 4, all right, which is a sphere of radius 2, okay? So that's actually the top equation. All right, so we got the top equation, and then, or that sphere equation, and now let's think about the cone. Okay, so the cone here, let's take it, and we've got, we know that the equation in rectangular is going to be z equals the square root of 3 times x squared plus y squared plus x squared plus y squared. Okay, and so what I get here is I'm going to get z squared, okay, equals 3 times x squared plus y squared. Okay. So now we've got to find the value for the cone. So we've got z equals the square root of 3 times x squared plus y squared. And if I rewrite that, that's going to equal the square root of 3 times the square root of x squared plus y squared. And that's r. Okay, so if you remember that, so that's z equals the square root of 3, and this is rho, which equals root 3r, which equals rho sine phi. Okay, so equals rho sine phi. What we're really going to expect, or what we really expect to have happen here, is we expect that we're going to just end up getting some kind of angle here. And so we're really looking for the angle there to end up giving us the value for the cone. Okay. And so if I do that, I'm going to get, so remember that z is actually equal to rho cosine theta. So this is, or rho cosine phi. So I got rho cosine phi equals the square root of 3 times rho sine phi. Okay. And so if I actually go in here and I divide, I'm going to divide through by rho cosine phi. That gives me 1 equals the square root of 3, and this is going to be tan phi. And so then tan phi is going to equal 1 over root 3, which is root 3 over 3. Okay? And so that means that phi will end up equaling pi over 6. Okay? And so that allows us to actually go out and find phi. Okay, so we found rho, we found the value for rho, we found the value for phi, right? The value for rho is going to start at 0 because we want all of those distances between 0 and 4. And then our values for phi are going to go between 0, and pi over 6. Okay? And then if you look at theta, your theta is going to just go from 0 to 2 pi. So theta will be greater than or equal to 0, less than or equal to 2 pi. So the box that I've generated here, B, my box, equals, okay, it's going to be the set rho theta phi such that rho is greater than or equal to 0, less than or equal to 4. Theta greater than or equal to 0, less than or equal to 2 pi. And phi is greater than or equal to 0 and less than or equal to pi over 6. So to find this volume, I'll set up a triple integral. Okay. And I've got 1. 1 is the function, so we just got rho squared sine phi. And we'll do d rho, d phi, d rho, d theta, d phi. All right, and our bounds then we're going to go from 0 to 4 because rho is first. Second is theta, 0 to 2 pi, and third is phi, so it goes 0 to pi over 6. All right, and let's just go in and solve this one to make our lives to just give us some practice actually solving a triple integral. So we're going to integrate with respect to rho first. So we've got the integral from 0 to pi over 6, integral from 0 to 2 pi, okay? And then we'll have rho cubed over 3 evaluated from 0 to 4. And then sine phi d theta, d phi, or sine theta, excuse me. Oh, excuse me, sine phi d theta, d phi. Okay, there we go. Now, this evaluated here, rho cubed over 3, evaluated from 0 to 4, is going to equal 64 over 3 minus 0. So it's 64 over 3. That's a constant, so we can bring that out. We'll get 64 over 3 times the integral 0 to pi over 6, integral 0 to 2 pi, sine phi d theta d phi. Now we're going to integrate with respect to theta. Well, there are no thetas in there. That's just a 1, so it's just have the constant 1. So that means that when we integrate, we get theta. So this will be 64 over 3, integral from 0 to pi over 6. And this will be just theta evaluated from 0 to 2 pi. And then finally d phi. So this ends up equaling 64 over 3, okay? And if we evaluate theta from 2 pi to 0, it's going to be 2 pi minus 0, which equals 2 pi. So we'll multiply this by 2 pi. And then we'll integrate 0 to pi over 6. And this should still be sine phi d phi. Sine phi d phi. Okay. And so consequently, what we'll get going from here to here, we're going to end up getting right, 128 over 3, and then the integral of sine phi is negative cosine phi, evaluated from 0 to pi over 6, okay? And that ends up equaling 128 over 3 times, and this is going to be negative, cosine pi over 6 is it's going to be negative square root of 3 over 2, right? Minus negative 1, minus positive 1, minus a negative 1, excuse me, negative 1. Okay, and so this ends up equaling 128 over 6 times 1 minus the square root, excuse me, 2 minus the square root of 3. Just took a common denominator of the 2. All right, and that ends up being the volume that you're looking for. All right, so what you can see here is that basically this figure, which would be just a bear to integrate using rectangular, what we can do now is we can just go in and we can say, okay, well, let's not do it in rectangular. Instead, let's go in and we'll change it to spherical. My sphere on the one hand, just a constant rho equals 4, and my my cone ends up being phi equals pi over 6, right? And the work that we did right here is to figure out what phi is. That actually is probably the trickiest part of the work that we got here. Once we've done that, we can set up our box and our limits of integration, and then it's just a triple integral, right, with funky Greek letters. So now let's take a look at another example. Let's look at different ways that we can actually kind of order our values using spherical. So let's say for example we have E as the region that's bounded below by the cone, z equals the square root of x squared plus y squared, and above by the sphere z equals x squared plus y squared plus z squared. Okay, and we're going to set up a triple integral in spherical coordinates and find the volume of the region using the following orders of integration. Okay, and actually we should make that z. So there's a little bit of an issue here. Okay, so notice that in this case, our sphere is not actually centered at the origin. And so we've got something, it's a little bit different. Our cone is pretty standard. It's not going to be too much of a problem for our cone, but our sphere is a little bit different. And it's actually centered at, some other points centered right there, okay? Not actually at the origin. So let's first start out, we're going to do our d rho, d phi, d theta. So for our sphere, we know that z is rho cosine phi, and x squared plus y squared plus z squared, that's equal to rho. Okay, so the curve z equals x squared plus y squared plus z squared, or that surface, is the curve rho cosine phi equals rho. Okay, if we go in here and we say, okay, divide through, or excuse me, and this is actually not rho, that's actually rho squared. Excuse me, rho squared. If we divide through by rho, we end up with cosine phi equals rho. Okay? So rho equals cosine phi is the sphere. And so that is the max volume for our rho. All right? And our min volume here is, notice that rho is going to end up being equal to 0. All right? So we're going to go from 0. So rho is going to go greater than or equal to cosine phi and less than or equal to 0. Or excuse me, other way around. 0 and cosine phi. Now, our cone, so the bottom end of our figure, right, the ice cream cone on our ice cream, is going to end up being, if we look at this, we've got the z equals the square root of x squared plus y squared. And if you're kind of paying attention to what we were doing inside of the last one, you'll notice that this thing here, this is rho cosine phi, okay? And this is actually equal to 1 times, and then this is the square, this ends up equaling z, or excuse me, rho sine phi, right? So that's r, 1 times r, and that equals 1 times rho sine phi, okay? And very similarly, right, if you notice, before we had a square root of 3, if you remember the last problem, it was a root 3. This time it's a 1. So what we get here is by dividing by rho cosine phi, divided by rho cosine phi, we get that tangent of phi is equal to 1, and that means that phi is equal to pi over 4. So phi is equal to pi over 4, because that's what tan phi of 1 equals. Okay? So our phi is going to go from greater than or equal to 0 and less than or equal to pi over 4. And finally, okay, our theta, okay, our theta is just going to go from 0 to 2 pi because we actually we're still going all the way around our figure. And so consequently, our box here, so theta goes from greater than or equal to 0, less than or equal to 2 pi. So our box here is going to be b equals rho theta phi, okay, and we're going to go from rho between 0 and cosine phi. Theta will go from 0 to 2 pi, and phi will go from 0 to pi over 4. So when we draw our integral for this volume, it's going to be first, since we're using d rho, d phi, d theta, we're going to get the integral, inside integral is going to go from 0 to cosine phi. The integral, since next up is we're going to do d phi, so d phi goes from 0 to pi over 4, and then we use theta, we're going to go 0 to 2 pi. And this will be then rho squared sine phi d phi, or d rho, excuse me, d rho d phi. Okay, now let's consider how it is that we're going to do d phi, d rho, d theta. All right, so this is a little bit trickier because it turns out that we got two figures here when we consider phi. When we consider phi first, what we're going to have is we're going to have this cone, okay, which we already know is phi equals pi over 4. We figured that out earlier. It's phi equals pi over 4. And then we also have this sphere here, okay? So we got the top part of that sphere. So what we're going to need to do is we're actually going to need to break this up into two integrals. We're going to need to break this up into two integrals. One, to integrate the cone. Two, to integrate the sphere, okay? So let's actually kind of set this up. Let's start out with phi and figure out what the bounds are going to be for phi. So for the cone, okay, for the cone piece, right, we're going to have, first the integral is going to go from 0 to pi over 4, all right, because that's the cone in terms of phi, and so that's going to be rho squared sine phi d phi, okay? And then when we look at the sphere, okay, the sphere, that top part of the sphere is given by rho equals cosine phi. So the bottom part of the sphere is going to be given by 0, right? Okay, because, or at least in terms of rho, the rho, that's 0, that's the line there, and then we're going to be possibly going all the way down to wherever it touches the sphere, okay? So what we'll do here to get rho is we're going to have that rho equals cosine phi, so that means that cosine inverse of rho is going to equal phi, okay? And so that's now our new phi. So this is going to go from 0, because we're going to start out at the z-axis, right? Okay, and then we're going to move outwards until we hit the edge of the sphere, 0 to cosine inverse of rho. And there's that. And then again, we're going to have rho squared sine phi d phi. Next up, we're going to need our d rho, okay, or need to figure out rho. If I look here now, what I've got to do is I've got to go in here and I've got to take a look, and I'm going to look at the cone first. Okay, so we're going to look at the cone first. And if I look at the cone first, there's rho equals 0. And then I need to figure out what this length is, because that's going to be my max length. Right? That's going to be my max length for rho. And so that's the point at which the sphere and the cone meet. So the sphere and the cone meet at that place. So I'm going to take that phi is equal to pi over 4, and that rho equals cosine phi. So we've got our two equations. Rho equals cosine phi, and phi equals pi over 4. We substitute in, we get rho equals cosine of pi over 4, and that ends up equaling the square root of 2 over 2. Okay, square root of 2 over 2. So that means that this integral, well, this integral over here, this actually should be over here, okay, is going to integrate from 0 to the square root of 2 over 2. And those are the values for rho. Okay, so there's the bottom end. And then also that means that this integral is going to have our bottom of root 2 over 2. And we're going to have to figure out what its top bound is. And again, remember, this is our sphere. Okay, so we need to think about what's the top part of the sphere. So on the one hand, we've got here that basic rho. There's rho. Okay, now we actually need to go up to the top part of the sphere. Okay, top part of the sphere. Now notice that top part of the sphere is going to have x and y equal to 0. So it's going to have x and y equal to 0. So I'm going to take my equation for the sphere. I've got z equals x squared plus y squared plus z squared. Right? X equals 0. Y is going to equal 0 at that point. So z is going to equal 0 squared plus 0 squared, which plus z squared. And the only thing, I mean, we're going to get z squared, or z minus z squared, equals 0. So either z equals 0, and then factor, that gives me z times z minus 1 equals 0. So z equals 0 or z equals 1. I come up here and I look at my figure. And I see my figure up top of sphere. That's got to be z equals 1 because down here it's got to be z equals 0. Okay, that's the other value. Great. So there it is. It goes from 0 to 1, or in this case actually rather root 2 over 2 to 1. And then theta, again, theta is not going to change. Theta is just going to be from our 0 to 2 pi in both cases. So we're going to have 0 to 2 pi, and then we'll have 0 to 2 pi here. And I'll add in my dr, d rho, and d theta, and then d rho and d theta. So actually it turns out this one ends up being a bit more complicated, although it might be easier to integrate. Okay, it might be easier to integrate. In this case, changing our bounds of integration forces us to think about the two different figures, right? Okay, on the one hand, right, we've got the top part which ends up being our sphere, and the bottom part which ends up being our cone, and those are actually different in terms of phi. Okay, in terms of rho, right, we just had to think about, okay, here's 0 going up to this top part of the sphere, right? That's just cosine phi, and so we only had to do that we only had to do a single integral there, okay? And then we figured out phi, and then we figured out theta. All right. So in this case, right, we'd have to look at this and ask ourselves, well, is it actually easier to do this integration? And it might be, but it's obviously somewhat more difficult to set up. So this completes my lecture on spherical coordinates. Earlier on, we talked a bit, we just kind of reviewed what spherical coordinates were. We talked a little bit about how we actually set up the integral, or how the integral gets set up, okay? And then we set up a couple of integrals to see what it looks like in order to have those bounds, how to set the bounds for cylindrical. For cylindrical, cones, spheres, okay, that's when you want to use the cylindrical coordinates, right? If we're using, excuse me, not cylindrical, spherical coordinates. We want to use spherical coordinates for cones, spheres. For cylindrical, we're going to do like cylindrical objects, all right? Sometimes spheres work out pretty well inside of cylindrical too, but generally, you know, like cones are those shapes, things that are circular or have like circular parts that are not necessarily spherical. And then rectangular is just kind of like our general catch-all. And oftentimes when you're looking at things that have rotational symmetry, you're going to want to change either to cylindrical or to spherical. All right, so that kind of wraps up this lecture on triple integrals and spherical.